Hello and welcome to this video. Today is Pi Day, so happy Pi Day everyone. We're going to celebrate Pi Day with some pie. As you can see, I have two pies on the counter. And also we'll do a fun calculus problem related to pies. That is the actual pies, not the mathematical constant pi. So I took out these two pies out of the fridge and I wish to warm them up in the toaster oven. But unfortunately, as you can see, my toaster oven is not big enough to put in two pies at once. I would have to warm them up one at a time. But of course, if I take out the pie from the oven, it starts to cool down again. So the question is, how can I time it correctly so that after the second pie is taken out of the oven, it has the same temperature with the first pie?
So this is the problem I wish to solve. I have two pies at room temperature TR. I want to heat them up in the oven at temperature TO, but only one pie can fit in the oven at a time. I put the first pie in the oven at time t equals to 0, then put the second pie in at time t equals to T1, taking the first pie out and sitting it on the counter. At what time t equals to T2 should I take out the second pie so that both pie will have the same serving temperature, Ts? To solve this problem, we will use a model called the Newton's law of cooling. This is what the law says. Let big T of little t be the object's temperature at time t. Then we let Ta be the ambient temperature, that is the temperature of the surrounding environment of the object, and Ta is treated as a constant. The Newton's law of cooling is given by the following differential equation. It says d big T over d little t is minus k times T minus Ta. Here k is a positive constant. It says that the rate of change of the object's temperature with respect to time is proportional to the difference between the temperature of the object and its surrounding environment. The constant k may have many influencing factors, such as the material of the object, the conducting medium, and the object's surface area, etc. This is a rather simple differential equation, and we can solve it immediately. Because Ta is a constant, we can rewrite the differential d big T as d of t minus Ta. So the function t minus Ta, we can think of it as a new variable y satisfy the differential equation dy over dt equals to minus ky. It has a well-known solution, namely the exponential function. So we have t minus Ta is t minus Ta when the time is 0 times the exponential decay factor e to the minus kt, which we can rewrite as T0, that is the initial temperature, minus Ta times e to the minus kt. Therefore, the solution to the Newton's law of cooling can be written as big T of little t equals to Ta plus T0 minus Ta times e to the minus kt. We will apply this result to our own problem. And here we have the graph of the solution. It has an equilibrium solution, T equals to Ta, the horizontal line. This is quite intuitive because if the initial temperature of the object is the same as its surrounding environment, then its temperature would just stay the same. When T0 is greater than Ta, we see that the temperature gradually approaches Ta as T goes to infinity. If T0 is less than Ta, then the temperature would gradually increase and approaches Ta as time approaches infinity. Going back to our 2 pi problem, we will first perform a qualitative analysis. The following graph depicts the scenario of our objective. Here we have 2 horizontal dotted lines that represent the oven temperature TO and the room temperature TR. The yellow curve is the graph of the function T1T, that is the temperature of the first pie with respect to time. It starts from the room temperature, and in the time duration 0 to T1, its temperature goes up as it is placed in the oven. And after the time little t1, the first pie is taken out of the oven, so its temperature begins to drop. The blue curve represents the temperature of the second pie. During the first time period, 0 to little t1, the second pie stays at the room temperature. It is placed into the oven at time little t1, so its temperature begins to rise. We hope to find the intersection of the two graphs at time t2 and temperature Ts. This means at time T2, both pies reach the serving temperature Ts. We will then set up the equations based on this graph. Now let's apply the Newton's law of cooling to each of the two time periods. For that, we will need to interpret the ambient temperature Ta and the elapsed time little t. First, let's look at the temperature big T1 at time little t1. This is the temperature of the first pie that has risen to after the time duration 0 to T1. During this period, the surrounding temperature is the oven temperature To, and the initial temperature is the room temperature Tr. So we have big T1 at little t1 equals to To plus Tr minus To times e to the minus k T1. We then find the temperature T1 at the time T2. In this duration, the surrounding temperature is the room temperature. The duration for cooling down is T2 minus T1. The initial temperature for this period is big T1 at little t1. Therefore, we have the temperature T1 at little t2 is equal to Tr plus big T1 at little t1 minus Tr times e to the minus k T2 minus T1. We may then plug in the temperature T1 at little t1 to simplify the expression. And this is a result, Tr plus Tr minus To times e to the minus kt1 minus 1 times e to the minus k T2 minus T1. And finally, we have the temperature T2 at time T2. It is equal to To plus Tr minus To times e to the minus k T2 minus T1. Because the second pie is in the oven in this time period, which lasted for a duration of T2 minus T1. We want the two temperatures at time T2 to be equal, and this gives us an equation. We can then simplify the expression to get a relationship between the time T2 and the time T1. The algebra is straightforward. And after some manipulation, we get T2 equals to 1 over k times the natural log of 2 times e to the k times T1 minus 1. This gives us a relationship between T1 and T2. However, we haven't used one piece of information yet. That is, the common temperature at time T2 is equal to the serving temperature Ts. For that, let's evaluate the right-hand side of the original equation, that is T2 at time T2, because it is simpler. We notice that in our steps of manipulation, we have an expression for e to the k times T2 minus T1. And that's exactly what we needed, so we make the substitution. So this is the result. We have an expression for Ts, in which the only unknown is T1. So of course, our next step is solve for T1. So after some algebra, we're able to isolate e to the k times T1, and the result for T1 is 1 over k times the natural log of To minus Ts divided by Tr plus To minus 2 times Ts. This expression for T1 is rather nice and can be considered as our final answer. It only involves the constant K and the three temperatures. We wish to write down T2 in a similar manner. From these two results, we can achieve our goal. The first one tells us T2 in terms of T1, and second tells us T1 in terms of the temperatures and the constant K. Substituting e to the kt1 into the first expression, and we get T2 is 1 over k times the natural log of To minus Tr divided by Tr plus To minus 2rTs. So this expression for T2, along with the formula for T1 earlier, gives us a ratio between T2 and T1. And therefore, in summary, we have the time T1, which depends on the three temperatures, To, Ts, and Tr, and the heat conduction constant K. And the ratio between the cooking times T2 and T1 only depends on the three temperatures. This concludes the solution to our problem. Now we know how to time the placements of the two pies so that they both reach the same serving temperature at the same time. Let's plug in some actual numbers to see what they look like. For example, let's use the following data. Suppose that the oven temperature is 175 degrees Celsius, and the room temperature is set to be 20 degrees Celsius, and the serving temperature is set to be 60 degrees Celsius. From these three temperatures, we can evaluate T2 over T1, which does not depend on the heat conduction constant K. and it turns out that T2 over T1 is 1.698. That means the second time duration, that is from the instance T1 to the instance T2, is roughly 70% of the length of the first duration, that is from 0 to T1. To find T1 itself, however, we would need to estimate the number k. For this, I looked up an online recipe. It says for heating a fully baked pie of 9-inch in diameter, I would need to place it into an oven of 350 degrees, I think this is Fahrenheit, for 15 to 20 minutes. And this allows us to estimate k. From the Newton's law of cooling, we have the following equation for k. 60 is the serving temperature, the final temperature. 177 is the oven temperature, equivalent to 350 degrees Fahrenheit. 20 is the initial temperature. And I use the average between 15 and 20 minutes as the estimated cooking time. From this, we can solve for k, which turns out to be 0.0168 with a unit of minute to the minus 1. Now that the k is estimated, T1 is just the natural log of 115 over 75 divided by k. So we have T1 is roughly 25.4 minutes given my oven setting. And the total cooking time T2 is 1.698 times T1 equals to 43.2 minutes. And that's the end of today's video. Thank you very much for watching. Once again, I hope you have a fantastic Pi Day. I'll see you next time. Bye.